Good day, folks. This is tutorial number 14 in a playlist that is called uh, Dynamics Scenario Animation and Simulation in 3D Experience. The problem that I'm going to be doing is a mass spring damper system, which is under free vibration. The, there is quite a bit of similarity between this tutorial and the one that I did in 13. The only difference is that I want to say a few words about the issue of the initial conditions of the vibration. Uh, in principle, no provision has been implemented where you can specify the initial conditions of the dynamic problem. However, in certain cases, this initial position, not the velocity, the initial position can be specified by uh, the reference length of the spring that is involved. For example, if you have a single degree of freedom system as shown that's consisting of a mass, spring, and a damper, which is not shown here incidentally, uh, which is sliding on a surface, for example, uh, notice that there is no indication of what the initial condition is except when you specify the reference length of the spring. What do I mean by that? Suppose I specify in the software that the see for a second, that the reference length is 0.45. Okay, suppose I do that. Okay, so suppose I specify that the reference length of the spring is 0.45. That drawing above tells you that the mass was actually displaced by 0.05 meter or 5 millimeter to the right and then released. Okay, now I don't need an excitation to specify an excitation in this problem because that initial displacement, which is buried in that reference length indicator, tells you the force of spring is going to supply the motion. Okay. By the way, I'm assuming this is cube of size 0.1, 0.1 by 0.1. So let me go back, look at this again. The very fact that the drawing shows you that uh, the distance from that edge of the cube to the wall is 0.5, and the fact that we're going to specify the reference length of the spring to be 0.45 meter means that that diagram on the top really is the mass displaced to the right by 0.05 millimeter. Okay? So this is how we bring in the issue of initial position into the problem, and it's released from rest, so it's going to be a free vibration. Now, let me remind you that I'm going to make a mass, and I have to declare the weight of the mass, but first I'm going to make it, assume that it's made out of steel, so that everything is generated, and then I can go and change that 7.77, the mass of that cube, into whatever I want, which is going to be 5 kilogram. And as far as the wall goes, okay, some based on the dimension that you put in there, some mass is generated, but that's totally irrelevant because that's not going to be moving. However, if you don't specify it, software will not run because the dynamic problem says that whatever parts you've got there, better tell me what the masses are. Okay. Now here's what I'm going to do. The stiffness of that spring is specified by this tab. 4,000 kilogram per second squared or Newton per meter. And the reference length of the spring, there's only one spring involved here, is coming from that tab there, and I put a 0.45. And when I model the geometry so that the left side of the cube is 0.5 meter away from the wall, that means already there is a force acting there because the spring has been stretched. Okay. Now, by the way, there is no damping. Initially, I'm not going to do any damping, but then I come back and put a damping value equal to this. Oh, incidentally, I'll be using the DASSL integrator over a 0.45 second interval. Now, you can do an analytical calculation here, and this is a very simple vibration problem. You can find the stuff in any vibration book. The period of oscillation for the damped oscillation, which you can see here, is going to be 0.227 seconds. Period of oscillation from peak to peak. And then the displacement and velocity and acceleration are calculated according to this formula, which can be obtained quite easily from vibration theory. And then I'm going to repeat that uh, with the damping. This was for a damping value of 56.57. Then I'm going to do it for a damping of 0. And obviously the damp period and the undamped period is the same because there is no damping involved here. So we're going to be comparing our results against these things. Okay, let's go ahead and do that. We go to 3D Experience, right click, insert a 3D part. What I'm going to be doing is, let's say I make the wall first. So let me call this, or the ground first. Properties, I'll call this thing ground. Ground and ground. Okay, say okay. Let's go make it. Double click on that. On that vertical plane, I will sketch the cross section of that piece that's supposed to be the ground. For example, I can do something like this. I'll put some dimensions later on. We'll clean it up in a minute. Okay, good. Now let's put some dimensions. For example, I'm going to make this thing 0.05. And it says, can I proportionally change everything? The answer is that yes. So that was 0.05, as you can see here. 0.05. Okay, and then this one is 0.05. These will affect the mass of the wall, which is irrelevant in our calculation, but I'll stick to my thingy. All right, so that's good. And this, why don't I bring this thing and put it against that wall? So this control that. Some dimension here, make it 0. Okay, good. And the length of this, I'll make it 0.7. So for example, that distance, I'll make 0.7 meter. So that's going to be my support. And then I'm going to pad it. Why don't I pad it symmetrically? I'll pad it symmetrically by 0.05 so that later on when I put the block on it, it's going to be 0.1 thickness. Okay. Now before I go any further, I want to do one thing, create a point over here because later on I have to create a spring. Oh yeah, this height I forgot to do it again. Let me go back here. There's some dimension that I forgot to put to make my job easier. I want this height to be also 0.05. Makes my job easier. Exit. Okay, now I'm going to create a point halfway between these two endpoints. So let's go and get a model point on a curve, and this is the curve, and halfway between, so ratio 0.05, 0.5 halfway. Oops, see now 0.5. Really? 0.5. Good, right there. 0.5 right there. You can see that the point right there. All right, so let's go and insert our block. So insert, right click, insert a 3D part. This I'm going to call the block. All right, and let's go make it. Double click on this. On a convenient plane, on that same middle plane, vertical plane, I'm going to draw a rectangle. Yeah, my rectangle is going to be, I'll draw it like this. Make it 0.1 on each side. So this is going to be 0.1. And this is going to be also 0.1. Okay. me see for a second. Let's go back in there. Okay, and then I'll make sure that this edge is half a meter away, from that wall on this left side. So go back here. Oops. Okay, so dimension between this line and that line to be 0.5. So already the spring is stretched. You can see that. All right, or will be stretched. Now exit and pad it symmetrically by 0.05. Very good. Okay, now I'm going to create a point right at the centroid of this, centroid of that face. So on the center of gravity, bad naming. So that's right there. Okay, and that's pretty much it. However, what I will do is I will also create a point, and you'll see why in a minute. I will create a point which is by 0.45 meter away from from this wall. Okay, so what do I mean by that? For example, let's go here. The different ways of doing it. For example, I'm going to create, let's do it in the ground first of all. We have to be in the ground because I want to measure from that point. So let's say measure a point with coordinates, and the coordinates are in this direction. Let's see now, in this direction, which is direction Y, it's going to be 0.45. You see right there, and the height is going to be whatever that height is from here. So I'll leave this thing the way it is, but I will come back and find out what is the distance. What is the distance between? What is the distance between? Well, let's actually find this distance. The distance here. Go ahead and measure the distance from here to here. For example, measure from this point to that point. And what I want is the height, which is 0.115 meters. See that? 0.115 meter. So that's okay. So now I go to this point and change the coordinate height of it to 0.115 meter. So that's going to be 0.115. It's going to push it. Oops. There we are. Okay. This 0.115. Very good. So okay, measure fade, that's okay, there's no problem. I don't need that. I just move that point up. That's fine. Okay. So the height, this is the same height as that. Okay. So here's what I'm going to do. We are done with an assembly. Look at what I've done. The ground, the wall, or not the wall, the block, and on purpose in the ground I created a point which is the same height as that, because later on I'm going to be measuring the distance between these 2 points and plotting it as a function of time. Okay, that's going to be the distance from the equilibrium, because remember this point has coordinate y equal to 0.45, which is the equilibrium point of the original equilibrium point of the thing. Now let me delete this measure because it's bothering me, so that I don't get that error message. Good. We go all the way to the top, By the way, why don't we go all the way to the top and fix the ground. So here fixing the ground. Okay, good. And now mechanical systems design. Why don't we create our spring? Here is the axial spring going between this point and that point. Okay, and for f of x, for stiffness in the x direction, In that length direction, axial direction, we put down 4,000. Oops, 4,000. And for reference length, we put down 0.45. Okay, and notice that my damping is 0 right now, so I'm going to be looking at a 0 damping case. Say OK. Or so a spring has been created here, will be created in a minute. What else do we need? Material, the properties, the masses. So we go to the weight definition. Everything is unknown, everything is red. So we go to the ground, click on the hyperlink to get the mass. Now notice that right now everything is 0. Everything is 0, you can see that. But if I click on this checkbox, it puts the properties of steel on it, and it's going to be something like that, 29.138. Please ignore in this slide, I put down some number here. Ignore this because the dimension must have been different for that. So that's totally irrelevant. Ignore it. Okay, so that takes care of this. Close this. Then click on the block. And once again, click on the hyperlink. Now here, if you check this box, it's going to give you 7.77 kilogram is the mass of that box. But I don't want that, I want 5 kilograms. So you put the cursor there and you change this thing to 5. And as soon as you do that, these inertial properties will change. You can see that they changed. Okay, so that's the correct mass. And we close this. Okay, very good. All right, now what we're going to do is go to the mechanical system experience. Oh, I forgot to create my mechanism. I forgot to create it. Cancel that. While I'm here, I'm going to create my mechanism. Here, mechanism representation. Say OK. Even if I didn't do it here, when I go to mechanical systems experience, it's going to do it for me. But I rather do it here. These are created and put in the mechanism. You can see that right now, right there. Okay. And now when I go to mechanical system experience, remember we got this message before, but there was a checkbox here say yes, created because I had none. But I don't need it here because there is already a mechanism. Very good. Now we don't need an excitation. We don't need any of these things. Because the spring is already stretched. We know that. So let's see now. We go to, for a probe, let's select a measure probe. How about a measure probe right there? Measure between 2 points. Between the point in the ground that I created. Remember I created this point in the ground? This point, not that point. This is the one on the wall. This point that I hit, if I say, show it to me, uh, well, we can select it. Oh, right there. You can see that right there. See this? Measure between this and the one for the block, the point on the block. Same point that I used to create the spring right here. So right now, yeah, so that's okay. Just give me that value later on when I do simulation. Let me hide this thing. Maybe I hide this from here. Well, it's okay. It just leaves there. That's okay. Now, we go to dynamic scenario, probe we created, parameter, that's the correct method. We go, what was this, 4.5 something? 0.45 second. We go for a period of 4.45 second. Say okay. Okay, and run it. This was no damping. It's going to be 2 oscillations because it was 0.45 second. Remember the period of this theoretical period was for 0 damping was 0.22 seconds. So when I did it over 0.45 seconds, it gives me 2 periods. That's why it meant twice, but that's okay. Check it out. Now, view scenario results. Plot the measured probe right there. You can see that. So notice that the period is roughly 0.22, roughly 0.22. That agrees with this number. And the oscillation at 3, for example, at point 3 is going to be negative 0.03 displacement. Let's go check there. Okay, at point 3, this is the measured distance. Okay, positive and negative doesn't matter, but if you want to know actually the position, then it's going to be basically it's going to be uh, on the left side of that reference point. Okay, so this is working fine, and the height of it, the maximum height is a point 1. So the amplitude is going to be uh, 0.5 0.05, right? 0.05 times 2 is going to, remember, the initial displacement was 50 millimeters. Okay, initial displacement of 50 millimeters. So the total distance peak to peak is going to be 1. So that's what 0.1 is. 0.1 is 0.05 here. 0.05 times 2. See, 0.05 times 2. Okay. Now let's go and add some damping here. I could have added a probe so that you actually get the positive and negative values, but that's okay. I'm not going to do that. Let's go ahead and change the damping. Right now we go to the spring. And if you go to the damping and put down the value 56.57, 57, and run it again, it's going to be damped oscillation. Okay, let's go check it out. The damped oscillation. Okay, and if you check this thing again, the period is very close to 0.22. It's going to be a little bit shorter. Okay, right there, it can be a little bit shorter. Theory predicts that it's going to be 0.2, actually longer, sorry, longer, 0.227. Okay, but it agrees with this quite well. So I'm measuring this. I'm measuring distance though. Just keep in mind that this is not the distance. This is positive and negative displacement from that equilibrium point. That's why it has positive and negative values. But if you go here, this is all positive. Okay, that's fine. So basically, we did what we were about. We were supposed to achieve. I wanted to show you that the initial position and initial velocity directly are not implemented in the 3D Experience's dynamic solver. However, dynamic scenario. However, for initial position at least, the reference length of the spring under consideration can help you to position the object, the mass, appropriately from its equilibrium location. All right, good luck.